let's jump right in. When we talk about coding, it's so easy to just lump it all together as one skill. But the truth is, it's a whole universe of different approaches, different mindsets, really. And today, we're going to look at what might be the biggest philosophical divide in all of programming. And it all boils down to this one question. When you sit down to write some code, what's your role? Are you a micromanager, spelling out every single tiny little step the computer has to take? Or are you more like a movie director, just describing the final scene you want and trusting your expert crew to figure out how to build the set and light it? Well, these two approaches have names, imperative and declarative. And honestly, the chef analogy here is perfect. Imperative programming is like handing a chef a super detailed recipe. First, chop exactly one onion, then heat the pan to precisely 375 degrees. You control how it all happens. Declarative is totally different. You just walk in and say, I want a delicious, savory chicken dish. You only describe what you want, not how to make it. Let's see what that actually looks like in the real world. So we'll start with the how, the world of imperative programming. And there is no better example of being in total, hands-on, granular control than a language like C++. Here, you are the absolute master of the machine's memory. And the main tool that gives you this power is the pointer. It's a pretty wild concept, actually. A pointer variable doesn't hold data, like the number 10 or the word hello. No, instead, it holds the address of where that data lives in the computer's memory. It's not the treasure itself, it's the treasure map. And this just shows you the incredible level of detail a C++ programmer has to think about. It's not just about having a treasure map. You have different kinds of maps for the job. You can use a flexible pointer that you can aim and re-aim wherever you want, or you can use a simple locked-in reference. Making these fine-grained decisions is really the heart of the how paradigm. So here's the crucial part. With pointers, you can change data from a distance. Just look at this little bit of code. We have a variable I that's holding the number 10. Then, using a pointer, we can reach into that exact spot in memory and change its value to 40, all without ever touching I directly. That's some serious power and, as you can imagine, some serious complexity. Okay, now I want you to take everything we just talked about and just throw it out the window. We're going to take a hard turn into a completely different universe. Let's talk about the what philosophy using a language called Prolog. And when I say it's a shift, I mean it. With Prolog, we stop writing step-by-step instructions and we start just describing a world. This quote really captures the breathtaking ambition behind this idea. I mean, listen to that. The goal isn't just to program in a different way. The goal is to get rid of programming as we know it. You don't write the solution. You just describe the problem, and you let the computer figure it out. So how on earth does that actually work? Well, it's surprisingly simple. It's built on three very basic ideas. First, you tell the program a bunch of facts, simple things that are true. Second, you give it rules, which let it figure out new stuff on its own. And third, you ask it questions, which Prolog calls goals. Let's start with that foundation, the fact base. This is nothing more than a list of things we know are true. Things like Luke is male or Sarah is female. Notice we're not telling the computer to do anything. We're just teaching it about the world. Now this is where it starts to get really smart. We can add rules that build on top of our facts. A rule like this one basically says, okay, computer, here's how you figure out if someone's a grandmother. A person X is the grandmother of Z if X is the mother of some person Y, and that person Y is a parent of Z. We've just taught the computer the concept of a grandmother. And finally, we get to interact with our program by asking it questions, setting goals for it. We can ask, is Luke male? And Prolog will look at its facts and say, yep, true. If we ask about someone it doesn't know, like John, it'll come back and say, nope, false. It's really just a simple conversation. But what about a more complex question, one that requires some real reasoning? With all the facts we gave it about who's a mother and who's a father, and that rule we taught it about what a grandmother is, we can now ask, is Jane the grandmother of Conrad? Now, in C++, you'd have to write a whole algorithm to trace the family tree. But in Prolog, we just ask. And this right here, this is the magic. Prolog has a built-in reasoning engine that just takes over. This visual shows you exactly what it's doing. It starts with our question. To answer it, it looks at the grandmother rule. That creates two new sub-questions it has to answer. The engine automatically searches, it backtracks, it explores every logical path until it pieces together the solution. We just described what we wanted, and the system figured out how. Incredible. Okay, so after seeing something that powerful, you might be wondering, why would anyone stick with that complex step-by-step how approach? Well, the answer is that imperative programming didn't stand still. It evolved its own powerful ways to manage all that complexity. And the most successful evolution by far is object-oriented programming, or OOP. The whole idea here is to stop writing one giant, messy list of instructions and instead build your program out of self-contained, reusable components, kind of like building with Lego bricks. It is the philosophy behind almost every app on your phone and every website you visit. Now, the key principle that makes all of this work is called encapsulation. An object basically bundles its own data together with the functions that are allowed to touch that data. It creates this protective little shell. That way, you can use a component without having to know all of its messy internal wiring, and you can't accidentally break it from the outside. OOP then gives us these two really powerful ways to organize our components to model the real world. We have inheritance, which models an is-a relationship. For example, a book is a type of publication. And then we have composition, which models a has-a relationship. A car has an engine inside of it. It's all about building structure. So we've seen three very different ways of thinking about code, giving super detailed steps, organizing those steps into neat little objects, and simply describing the final goal you want. What's the big picture here? What does it all mean? Let's just break it down one last time. You've got your classic imperative style, which is all about telling the computer how to do things, right down to managing memory with pointers. Then you have object-oriented programming, which takes that how and organizes it into tidy, reusable components. And finally, you have the declarative approach, which just flips the whole script and lets you describe the what, relying on a smart engine to do the hard work. So, which one is the best? Well, here's the thing. That's absolutely the wrong question to ask. None of these is universally better than the others. They are different tools for different jobs. If you're building a high-performance video game engine and need total control, you want imperative. If you're building a massive, complex application, you need the organization of OOP. And every time you type a search into Google, you're using a declarative system. And that leaves us with a pretty fascinating final thought. This very old debate in programming between how and what is suddenly more relevant than ever. As we build these incredibly powerful AI systems, we have to ask ourselves, is our job to meticulously program how they think step by step? Or is it to simply define their world, set the rules of the game, and clearly state the goals we want them to achieve? The entire future of programming might just depend on that answer.